Hi guys, what we're going to do now is we're going to look beyond the strong acid, strong base titration curve, and we're going to look at a variety of different problems that they tend to ask you when it comes to titration curves that go beyond the strong acid, strong base. So remember, before we move on from that, let's just take a moment and talk about strong acid, strong base. If you're talking about a strong acid, strong base situation, then what you're saying is that you have some sort of a curve like so, where the equivalence point of that curve is such that it should be right at about a pH of 7, because if you have equal amounts of strong acid and strong base, strong acid is as strong as it can get, strong base is as strong as it can get, and they neutralize each other completely. So your equivalence point, which is again where the moles of the acid and the moles of the base are going to be the same, then it should be right at a pH of 7, because the strong acid and the strong base neutralize each other. But what if you're talking about a situation where you have one of the species is strong and one of the species is weak? Now, we talked a little bit about this before in one of the other lectures. If you have the acid, for example, that is strong and the base that is weak, even if they're equal, they're not really equal, because the acid is stronger. The acid is a 100% all the way infinite K value, all go no quit acid, and the base is So consequently, even if they are equal in amounts, they are not going to be equal in effect, because the acid is going to end up being stronger than the base. So consequently, what ends up happening is, if we were to look at a typical titration curve here, where your pH value is right at 7, and again, that is a typical strong acid, strong base situation, what's going to happen is that the acid is going to win. And if the acid is going to win here, then what we should see is we should see a decrease, a drop in the equivalence point pH, because the acid is going to end up being stronger than the base is. So what's going to end up happening is you're going to end up with a graph that looks a little bit more like this, for example, and where you still have the same kind of a curve, and there is still the point of inflection that is right here. So again, the point of inflection doesn't change, but the point of inflection is now no longer at 7. The point of inflection is below 7, because the acid is a strong acid and the base is a weak base that is there. So consequently, if you have a strong acid, weak base situation, you are going to see the same shaped curve. Everything is going to be the same, except your equivalence point is not going to be at 7. It is going to be a little bit below 7. How far below? Well, that depends on how weak the base is. The weaker the base, the further below 7 that pH is going to end up. So if you have a tremendously weak base, then you'd be talking about, an equivalence point that was, more along these lines. If you have a base that's weak but not quite so weak, then, maybe you're talking about an equivalence point that's just a little bit below 7. But regardless, if you have a strong acid, weak base situation, then you are going to end up with the equivalence point that is below 7. So that stands to reason then, what would happen if you end up with a situation that is a strong base but a weak acid? Well, you're going to end up with the same thing, except that it's going to be opposite. So instead of a strong here at 7, because again, that would be a strong situation, the base is going to win even if they are equal, and if the base is going to win even if they are equal, then you're going to end up with a situation where your equivalence point is going to be slightly above 7, like so. So regardless of how what substance you use, you're going to end up with a titration curve. There's going to be a point of inflection, which is your equivalence point. It's just that in a strong situation, that pH equivalence point is going to be at 7. If you have a strong acid, weak base, then the pH equivalence point is going to be below 7. And if you have a strong base, weak acid, then you're going to have an equivalence point that is above 7. The nice thing about this is in all of these cases, you still have that the moles of the acid is equal to the moles of the base. So this then lets us do a bunch of different other types of problems that they could throw at your way. So for example, it says, if 1.25 grams of an unknown weak acid is titrated with 0.25 molar sodium hydroxide, what is the molar mass of the unknown acid that is there? So first of all, let's notice a couple things here, that this is a weak acid, strong base situation. So your equivalence point is right around there or so. And so please note that, again, your equivalence point is above 7. There's 7, so that makes sense. But regardless, you still have the moles of the acid that equal the moles of the base that is there. Now, what is it that they want? They want the molar mass of the unknown acid. Or, in other words, they want the molecular weight. The molar mass, the molecular weight. Well, remember that this is the number on the periodic table. So that is the number of grams per mole. So that's all they want. They want to know the grams per mole. Well, let's see. Do I know either of these pieces of information right now without any effort whatsoever? Well, yeah, check it out. They gave us in this problem 1.25 grams of the unknown weak acid. So I have the top number right now with no effort whatsoever. This is 1.25 grams. They gave that to me. If I knew the moles of the acid, I'd be done. Well, I don't know the moles of the acid, except that I do know the moles of the acid. And the reason I know the moles of the acid is because I have a titration curve. And if I know the titration curve, I know the equivalence point. And what do I know about the equivalence point? I know that the moles of acid and moles of base are the same at the equivalence point. So a rough little look-see looks to be that's around 18 milliliters or so. So that looks right there that we are at about 18 milliliters of 0.25 molar sodium hydroxide. So if I have 18 milliliters of 0.25 molar of my strong base, then, well, I know the moles because I know the liters and I know the molarity. So again, this is 0.018 liters times 0.25 molarity. And so if I get out my trusty calculator here, 0.018 liters at 0.25 molarity, that's going to get me 0.0045 moles of my base. And what's so special about that number at that point? Well, if this is 0.0045 moles, then at that point this is 0.0045 moles as well, because the whole point of the equivalence point is that they are the same. So that means down here I have 0.0045 moles down here. So 1.25 grams divided by 0.0045 moles gets me a molecular weight in the neighborhood of about 278 grams per mole. So that might look really, really complicated, but ultimately it's not. You go straight to the equivalence point, you figure out the moles, you plug it into your molecular weight, your molar mass equation, and you're done. You're good to go. Let's try another one of those. Example number 2 here. You've got 4.75 grams of a weak base, and you're titrated with 1.5 molar hydrochloric acid. What's the molar mass of the weak base? So once again, let's just double check to see what's going on here. I've got a weak base being titrated with a strong acid. It really looks to me that your equivalence point is around there. And please note that your equivalence point is less than 7 because it's a weak base and a strong acid. So that's good to know. And then from a quick look-see, it looks to be, whoopsie, wrong one, looks to be somewhere around, 10 milliliters, maybe 9.5 milliliters, maybe 9 milliliters. What do we got here? Let's see, that looks to be, call it, let's see, 8, 10, we're going to call it 9 milliliters. We're going to keep it simple, and we're going to call it 9 milliliters here. So we're going to call that guy 9 milliliters. So what have I got? I have got 9 milliliters of 1.5 molar hydrochloric acid at the equivalence point that's there. And again, a little judgment is involved here, and that's fine. But I want the molecular mass. I want the molar weight. So the molar weight is going to be equal to the grams per mole. They already told me the grams up here. They told me that it was 4.75 grams of the base. So I know that already. So this is 4.75 grams all I need to know is the moles. Well, I know it because I know that there is 0.009 liters of 1.5 molarity. So 0.009 liters of 1.5 molarity gets you 0.0135 moles. And that's the number that's going to go down here, 0.0135 moles. So 4.75 divided by 0.0135 is going to get you a molecular weight in the neighborhood of about 352 grams per mole. So all of that are some very typical, straightforward problems that they could ask you about titration curves that are not necessarily strong titration curves. Additionally, they're going to ask you about indicators. So what are indicators? Indicators are different chemicals that change colors at different pHs. There are some very famous indicators that we know of. Phenolphthalein, universal indicator. Probably the most famous indicator of all time is litmus. Litmus is the stuff that goes from blue to red, and in fact, it has become so common in our language that a litmus test is just described as a generic test to say whether or not something is or isn't something. This is a litmus test to see if they're liberal enough. This is a litmus test to see if the bread has risen enough. But technically, litmus is an indicator. It's the stuff that goes from blue to red at a particular color. And why do I bring this up? I bring this up because you want the indicator to indicate where the pH is really radically changing, and in a perfect world, you want an indicator to tell you where the equivalence point is. Now, if you have a strong situation, you really have quite a pretty big leeway here, because in a strong situation, your vertical part of the graph is so large here that you don't necessarily have to pick one of these indicators that are up here that changes at a pH of 7. You really could get away with quite a few of these different indicators. You could do methyl red, because even though methyl red changes at around a 5.5, that 5.5 is essentially at the same point as your equivalence point. You could have picked thymol blue, which changes around a 9, because again, even though it changes around a 9 and it's up there, it's still on the same vertical portion of this, which is what you'd be interested in down here, right? So there is that. Now, where you get into trouble is where you start shifting the titration curve up or down a little bit if you're talking about a strong, weak situation. So if you're talking about, for instance, this guy here, thymol blue works great as an equivalence point here because it is on the vertical portion of the graph. But take a look at where methyl red is. Methyl red is changing pH right around here or so, and that is not on the same vertical portion of the graph as this other one here is. And so consequently, if you were to use methyl red in this circumstance, you would get an equivalence point result that is off. So it's really simple. All they're going to do is they're going to give you a graph or a situation, and they're going to ask you which indicator is appropriate to use. All you've got to do is pick an indicator that changes on the vertical portion of your titration curves. As long as it's anywhere on this vertical portion here, you're going to be fine. But if you pick a indicator that changes down here or down here or down here on the graph, that is not going to be an appropriate indicator to use. So any indicator that changes in the vertical aspect of things here, where that inflection point is, then you'll be in good shape. So oftentimes they will not give you the information like this or like this or like this. Oftentimes what they will do is they will give you what's called a pKa value. And the pKa value, and you can see those listed right here, the pKa value is where on the graph the indicator changes color. So for example, if you were to look at something like phenol red that has a pKa of 7.4, then you'll notice up here on the graph that at about a 7.4, is where phenol red is going to change color or so. So here's your phenol red right there, and it changes at about a 7.4 there. So the pKa is just an easier way for them to tell you and arrange it so that they don't have to give you a big old graph like this. So if they give you a pKa number or a pKin number there, they give you a pK number for the indicator, then all that is doing is telling you where on the pH scale that thing changes color. And so you'll want to pick one of the indicators that has a pK number here that is on the vertical portion of your graph. So take a look at this. It says, of the following indicators, alizarin yellow R, bromphenol blue, and phenol red, which one is going to be the best for this titration curve? Well, let's take a look at them. Alizarin yellow R has a pKa of 11. So this guy here has a pKa of 11. So if we were to take a look at 11, 11 is up there. So there's an 11. And then the bromphenol blue is right here at a 4.1. So a 4.1 is about here. And that's about a 4.1. And then phenol red was here at a 7.4. And so a 7.4 is about here on the graph, like so. So which of these is the best to use? Well, definitely this guy down here is not a good choice. He's a terrible choice. This guy up here at 11 is not terrible, but he is beginning to get into that curvy portion of the graph here. So again, in a perfect world, you want something right here at the equivalence point. And this guy's beginning to get into the curvy portion of the graph that's there. Probably your best one is this guy here at the 7.4, because it appears to be the indicator that's going to change on the closest to the vertical aspect of things. So all you want to do is pick one that is closest to the vertical port of the inflection point that's there. Number 2 says, from the list on the previous page, pick an indicator that would be useful for this graph. Really, you have a wide range of things. You can kind of pick anything that goes kind of from about here to about here. So pick anything that goes from about... So anything here that goes from about, oh, I don't know, what is that? 6, 5, 4, 3. So anything from about a 3 to about a 6.5 or a 7 or so. So that's kind of your range here. Your range on this appears to be from about a 3 to about a 6.5 or a 7 or so. So maybe 3.5 to 6.5 would be your sweet zone, right? Your swing zone. So anything in that 3 to 6.5 zone. So if I came back up here, as long as it was probably in this zone to this zone here, any one of those would probably do for an indicator for this particular graph that is there. So the important thing to know overall is that if you are a strong, it's going to be an equivalence point at 7. If you are strong, weak, it's either going to be above or below 7, depending on which one is strong and which one is weak. You now have another tool in your pocket to determine what the molar weight or the molecular mass of a substance is, and you know a little bit about how to pick an appropriate indicator based upon where that indicator would fall for the particular titration in question.